Okay, so we're a little bit late for the Olympics, but I want to talk about statics and torque for an Olympic gymnastics move called the Iron Cross. So the Iron Cross is this move where you have these rings hanging down from ropes, and the gymnast holds onto the rings and just holds themselves up just by with their arms horizontally, holding onto the rings like this. And so this is a really hard move. We would love to have demoed this in the class, but it's not something I can do, and it's hard to do. So we're going to learn about why that's really hard by looking at forces and torques. And the first question is, when you do this move, just by doing a free body diagram on the person, what is the tension in the ropes? So, right, you have just the gymnast here, and they're holding on to some ropes that are going up like this, right? Ropes are going up like this. And from each rope, there is a force of tension, right? There's a force of tension from each of them, so there's two forces of tension. And then you also have, from your center of mass here, you have mg going down. And let's just quickly do our sum of the forces in the y direction is equal to MAY. And here, you're just standing still. So AY equals 0. And the sum of forces are 2 force of tension, positive because it's up, minus mg down is equal to 0. So the force of tension is equal to mg over 2. So that's the tension in the ropes. Now, what you're really interested in is what's going on with the muscles in the gymnast, because that's what's making it so difficult. You know, they work out so their muscles grow and so they can actually do this. And so we want to know what are the forces that are going on in those muscles. And so if you look at this little picture here, it shows the muscle that is doing most of the work here. So that's not the work in terms of this class, but in terms of biological work. It's actually, doing this contracting. And so the main muscle is the teres major muscle. And what makes this so hard is that so let's draw the arm something like this. And then the teres major muscle connects right around here back to your body. And the distance from the joint right here to where the teres major muscle connects, let's call this distance d. It's a very short distance. So in order to keep your body from moving or to turn your arm, you need a really big force on that muscle, because the distance to the pivot point, your shoulder, is so small, because you multiply those to get the torque to make it turn, or to stand still in the case we're about to see. And so what we can do here is we can do a free body diagram for the arm itself. So we did a free body diagram for the person here, and if we do a free body diagram for the arm, we can figure out what's going on with the forces just attached to the arm. So we have this force down, so we'll call this the force of the muscle. Force of the muscle. And then we also have, since the end of the arm is right here, we know that that's where the rope is, they're holding on to the ring right there. So we have an upward force of tension from the rope. And then the question is, are there other forces going on here? We have to have all the forces in order to do this free body diagram correctly. And as always, we will have a force of gravity. So there's a really small, so this would be the m of the arm times gravity. But since we already know that the force of tension is going to be m, this is the m of the body, times gravity divided by 2, we know that the M of the body is much bigger than the mass of the arm, and so since I know that this force is really small, we could put it in there, we could keep it around, but it's really small compared to the other forces in the problem. So for now, we're just going to forget about this altogether because it's small. So just don't worry about it. I just wanted to show you how to do a problem like this. In reality, you would have that force in the diagram, but just for this exercise, let's leave it out. Okay. So are there any other forces on the arm besides the tension force and the force from that muscle? Well, there actually must be, because the force from the muscle seems to be pushing the left side of the arm down, and the force from tension seems to push the right side of the arm up, and that means the arm would rotate if there isn't any other force. So where is that other force? Well, is the arm connected to anything else? Well, yeah, it's connected at the shoulder. So the shoulder bone and cartilage and all of that. So that's putting some forces on the arm also. And what are those forces? How big are they? In what directions do they go? Well, we don't really know how big they are or exactly in what direction they go. So what we do know is that it looks like we have only, in the x direction, we only have one force that's pushing this direction to the left. So we know that we will have the shoulder, the force from the shoulder in the x direction going that way. And then I'm not sure if we'll have more force up or down on the arm without the shoulder. So I'm just going to draw the force from the shoulder in the y direction up. And if it turns out when we go and calculate that, which we're not going to do here, but if you were to go calculate it and you find that it's a negative number, then we just know the arrow will have been in the wrong direction. So this is a good approach when you don't know how big the forces are. Just draw one in the x direction, one in the y direction, and then if you end up getting a negative sign, you know that you drew the arrow in the wrong direction. So now let's first choose a pivot point and then calculate the torques. So since there are two forces at the joint that we don't know what they are, and what we're actually looking for here is we're going to be looking for the force in the muscle, because we want to know why is this so difficult, how much force is going on in that teres major muscle. What we can do is we can choose our pivot right here. So this is going to be our pivot. And that'll be clear why we're doing that in a second. So we're going to sum up, so this is the equation we'll use, the sum of the torques, and since this thing isn't rotating at all, the sum of torques has to equal 0. And in this situation, so recall that a torque is equal to R cross F, where R is the vector from the pivot to where the force is acting. And so here, if we choose our pivot right there, then our R for both the force from the shoulder in the y direction and in the x direction, that torque is going to be 0. So we only need to worry about the torque from the muscle and the torque of tension from the rope on the end of the arm. And so let's just sum up both of these torques. So our R for the muscle is going to be this D. So we can write this, remember, as just the magnitude of R times the magnitude of F times the sine of theta between the two vectors. And so for the muscle, that's D times force of the muscle times sine of, and then this right here is theta, sine of theta. And then we have plus, let me just box this off so we don't get confused here. So this is going to be plus, and then we have the vector to the force of tension is this right here, and the length of the arm is L, so that's going to be L, and then force of tension, and we have a 90-degree angle between them, so that's sine of 90, which is just 1. So it's just this whole thing is now equal to 0. And then we just need to solve, if we're looking for how big the force in the muscle is, we just look for force of the muscle is equal to L. There's one small thing that I haven't put in here. So I wrote down the two torques, and just before I do this, I want to make sure I have all the signs right. So we defined the positive torque to be in the counterclockwise direction around the pivot, and the negative torque in the clockwise direction. And so the torque from the force of tension is going to be in the counterclockwise direction. So this was the right sign. But this one here is going to push the arm in the clockwise direction. So we know that this is actually negative. So then we can, when we solve for the force from the muscle, we get the following expression. D sine theta. So just move this to the other side and then divided by d sine theta. Okay, now in C over here, we're given that d is equal to 1/20th the length of the arm, and we're given that theta is equal to 120 degrees. So what we can do is just plug in our numbers here. So we have L, and then do we have what L is? Okay, we don't have what L is, but let's see if that matters. So we have L, and then force of tension is going to be mg over 2. So what we calculated in part A. And then we have D is equal to L over 20. Okay, this is good, our L's cancel. And then we have sine of 120 degrees. And then now, it's pretty easy to see we're going to have a big number. What this works out to be is about 12 mg. That's 12 times the weight of this gymnast, and that's the force in the muscle. It's 12 times his weight. And so that's why this is so hard to do, because since the muscle attaches really close to the shoulder, the muscle has to apply really big force, and that means your muscle has to be really strong to do the iron cross. Now just quickly, the bonus says, what would be the tension in the active muscle if the distance, this Rm, which was 1/20th of L, approaches 0? So if we attach the muscle really close to the pivot, and as you get closer and closer, the muscle has to be stronger and stronger to counteract that small d or small Rm, and so it would have to approach infinity, the muscle force or the tension force in the muscle. So that was just one quick example of how to use torques and statics to figure out what's going on in some gymnast's body. I hope it was helpful.